serve the evil of people.
And now we're live. All right. So yesterday, Zayden taught you guys, and I wish I had recorded it. It would have been so fun, right? Yeah, he is a good teacher, right? I gave him self-development for it, gave him about 6 points. We'll go over self-development at the end of class. I have not graded the self-development you did on Wednesday, obviously. I'll put that in this weekend, and then I'll give you the new totals. At the end of class, if we have time, I'll tell you the totals you're at right now for self-development. Remember, you need 20 per semester. Speaking of semester, the quarter is ending very soon, which means if you want to do a retake, you have to do it not just in time before the quarter ends, but also in time for me to grade it before the quarter ends. That way I can put it in. Otherwise, grades get locked. Yes?
When's the end of it?
I don't know. Who knows things?
March
15th or something.
I'll take one Monday.
You have 2 weeks. Next week and the week after that, and I think that's it.
I'll do it too.
Fourth quarter, speaking of which, will go by so fast for 2 reasons. 1, spring break. 2, finals. That'll take up some time, right? Okay. And then 3, a lot of end of the year stuff like testing, like ACT, PSAT, and all that crap, right? Fourth, look, it was up to me, you would. But note that fourth quarter is going to fly by. Okay? So do not get behind on stuff. You want to be ready to go for that final ahead of time, okay? We'll start talking about student portfolios hopefully in the next 2 weeks, okay? Most of your student portfolios should already be done from last semester. If it wasn't, it's because you slacked, and now's the time to really catch up, okay? All right. So yesterday. All right, guys, shut up. So here we go. Yesterday we said if triangles have the same height, then their areas are proportional to their bases. And this is because the area of one triangle is half base times height. Well, if they have the same height, when you divide them, the heights cancel, become 1, and the halves cancel and become 1. And all you're left with is the bases. Remember that from our okay, cool. That was our first lemma. So I said these two triangles, here and here, have those bases so they go together, right? These two triangles also have the same height, and they have these bases, so they equal A over B. So we have 3 things equaling each other. By our first lemma, if we have something over something equals something over something equals something over something, we're allowed to take 2 of those and put them together like this and have them equal the third guy. Okay? Now we proved that for our first 2 lemmas. That's just a thing you can do. Is everybody cool with that so far? Not 100%, but enough to be like, okay, sure, if you say so. Yes, no, maybe? Now, what's cool about this is that this minus this, what that is this big triangle here minus this triangle here, the one at my finger's inside. And what's left over? This triangle. So in other words, when I say this minus this, what I really mean is this triangle, triangle ACG. So ACG is going to equal A, and BCG is what you get when you subtract these. That's the triangle that's left over, right? This big triangle minus this triangle leaves triangle BCG left over. So those 2 over each other equals A over B. Yes?
Is this going to be one of those things where like we get it after 2 weeks? I don't think I did.
Now, do you see right now that this minus this gives me this triangle? And this minus this gives me this triangle? So by substitution, this triangle over this triangle equals A over B? And that's what I wrote here? Okay, awesome. That's what I need you to see. Then after I get that, that's the first half of the proof. Then I can do, by same dumb logic, I can do the same thing for all these other guys, right? And what's this minus this and that minus that? It's this. These 2 triangles left over. And what are these triangles subtracted? It's these triangles left over. Okay? Trust me on that. So now I know what A over B and C over D and E over F equal. So when I multiply them, like it said in the beginning, that I wanted to prove, what is A over B? Well, it's this stuff. What's C over D? Well, it's this stuff. And what's E over F? Well, it's this stuff. And if you notice, these 2 triangles are the same, right? What's anything divided by itself? 1. These 2 triangles are the same.
Well, there's also China.
Anything divided by itself is? 1. These 2 triangles are the same. So anything divided by itself is. So we have 1 times 1 times 1, which proves that this equals 1. So if we have a bunch of Cevians that are all concurrent, then we get all these weird triangles, right? And I can prove that A over B times C over D times E over F equals 1 when that's true. So if the Cevians are intersecting, right, then we know that this relationship holds. Are we okay with that? Mostly okay? Nelly? Mostly okay with this idea?
Oh yeah.
Okay. The key is to understand this first part. And then you get this alphabet soup down here, but it's just the same dumb crap done with the same different triangles, right? So I've drawn something out to show you. So same diagram, just bigger. If you hadn't got it before, now's the time to look. Red triangle and blue triangle have the same height. You with me? Which means their areas should be proportional to their bases. That's what I wrote down here, okay? Green triangle and pink triangle have the same height, so they should be proportional to their bases, which also happen to be A over B, right? So I can take these two and subtract them like that and get the middle guy. That's our first lemma, right? It allows us to take things like this and do that. But what is red triangle minus green triangle? Red triangle minus the green triangle is the orange triangle. So whenever I see this, I can put an orange triangle in right here,
Speakers are all poopy.
right? And whenever I get blue triangle minus pink triangle, that's yellow triangle left over. I colored it in purple here because I don't have a yellow pen. Sorry. So this equals that, and that equals this. So therefore, these two triangles must go with A and B. Now I can do that same dumb thing, same dumb logic, right? With C and D and E and F. So I'm going to turn the page. Same triangle. Now I made my blue triangle, my red triangle, these two triangles. And they go with their bases. And these go with their bases. So when I subtract them, these are what's left over. And they should go with their bases. Do you see that? Macy, are we better on this or no? Blue minus pink gets me yellow, so yellow should go with D. Red minus pink, orange, colors are hard. Red minus green gets me orange, so orange should go with C. Okay?
What do you mean like yellow should go with D and orange should go with C?
So this yellow triangle right here is going to be proportional to its base, and this orange triangle will be proportional to its. And here's why. We know that the blue and the red have the same height, right? And we know that if they have the same height, their areas should be proportional to their bases, right? So blue over red will be D over C. Okay? These two both have the same height as well, right? The pink and the green. So their area should be proportional to D over C, right? Well, what is blue minus pink? It's this. And what is red minus green? It's this. So these two are going to be C over D. And the reason for that is because we know that when we have something like this, we can rewrite it with these two being subtracted, and we get the middle guy. So when I subtracted those triangles, they also go with A over B. What's left over, right? So what's left over goes with C and D.
So like the thing that connects to the yellow triangle with C or the orange triangle or the yellow triangle with D, the orange triangle with C is the pink triangle and the green triangle.
Yeah. So the big blue minus the pink is what's left over, right? It's this guy. And we know blue and pink will both go with D. So when I subtract them, I should say that the thing left over goes with D. And the reason for that is we're allowed to say by our first lemma, if we have a bunch of ratios equaling each other, then we can take two of those like this and get the third guy. So because of that property, this becomes that becomes that, and these must also be A over B. Okay? It's a weird property to go from this to this, but it's true. It works. We proved that as our first lemma.
So like how is can you go back to that?
Yeah.
How is when it says the pink is it like the pink one minus the green one?
Red minus green.
Okay. Oh wait, yeah.
Does that make sense?
Yeah.
What's left over is orange?
Yeah.
Okay. Same thing here. I just made my red and blue triangles, these ones, because they go with C and D, right? And that's how I get these guys to go with C and D. Now I'm going to do the same thing for E and F. So I'm going to make this triangle and subtract these two, and what's left over will go with E and F. Let me show you that, okay? You see it? Red minus green gets this, so it should go with E. Blue minus pink gets this, so it should go with F. Okay? That's the idea. Now, if you want, I can provide you extra copies and you can color to make sure you're matching up the right stuff. But in general, doing it on here isn't too bad. These two must go with A and B. These two must go with C and D. And these two must go with E and F. And the reason we wanted to get those together is if you notice, look at this triangle right here. I'm going to turn the page. We use that triangle again, don't we? So there's overlap, which is why when we divide, right, things go away. Look at this triangle right here. we've used it already here. So there's overlap and things will go away. And look at this triangle here. We used it in the beginning for this guy. Right? So when we multiply, thing on top, thing on bottom are the same. They go away. And we do that 3 times, and we get 1. How are you feeling? Okay? It's a lot of writing, but really it all comes down to this first part. That's it. These triangles have base A and base B. These triangles have base A and base B. When you subtract them, they should still equal base A and base B. What is it when you subtract them? Well, it's this triangle and this triangle. What's the name of those triangles? Well, it's this. Then by same dumb logic, okay? Same dumb logic, it applies for all the leftover triangles. Excuse me, for C, D, and E, F. Then I multiply them all together, multiply these all together, 1. Why did I multiply them? Because I wanted to prove that that equals 1. So I took my A, B, C, D, and E, F and multiplied them all together. And that's what it should equal. Then I cross off a bunch of stuff and I get 1. Okay. If you're feeling about 50, that's really good. If you're feeling better than 50, that's excellent. Okay. Today, before we get into this is Ceva's theorem's converse. Remember, Ceva theorem says that if they're all concurrent, then we get the A over B times C over D times E over F equals 1 thing, right? This is saying if we're given this about a triangle, then that means the Cevians must be concurrent, that these lines must all intersect at one point. Okay? Now we need a different method to solve this than we've used previously. And that method is called proof by contradiction. So if you grab your proof by contradiction worksheet, we'll get into that and show you what that looks like. Okay? Here's how proof by contradiction works. It's really hard to prove something true, right? Because you got to prove it true for everything, right? Prove that every other number is always even. I got to prove it for every single other number, right? That's a lot of numbers to do. So what we do is we prove that it's impossible for it not to be true. So what we do is we assume the opposite and prove that it would be absurd for that to be true. So therefore, the other thing must be true. Let me give you an example. It's really hard to prove that today is not Saturday. It's very hard to prove that. But what if I assume today is Saturday? Well, that would be absurd because why? Because you wouldn't be at school. So that contradicts my assumption, right? You guys are at school, and I assumed it was Saturday. So obviously it's not Saturday. So it must be some other day, right? That's proof by contradiction. I proved that it's impossible for it to be Saturday, right? So I proved that it's impossible for this to be true. Therefore, the opposite must be true. You didn't have me for algebra, so this looks like garbage to you, okay? It says we're trying to prove 2 positive integers always have a positive sum. So think of 2 positive whole numbers, essentially, right? Like 2 and 5, 6 and 4, just no fractions allowed, no negatives allowed, right? Think of 2 numbers, add them together. Did you get a positive number? Of course you did, right? Like 5 and 2 is always going to get you 7, right? It's going to be a positive number. It's never going to go negative. So I'm saying, given that we're thinking of 2 numbers that are positive, that's all that means, okay? Positive whole numbers is what that means. Then when I add those numbers up, it should be greater than 0, right? So that's really hard to prove because I got to prove for every single number. So what I'm going to do is I'm going to assume that when I add those 2 numbers up, that it gives me something less than 0, otherwise known as negative, right? So I'm going to say assume A plus B is less than 0. Assume that, right? Assume when we add them together, we get a number less than 0, meaning negative, right? Assume that they add up to something less than 0. Now, I'm going to show that this is absurd. Could not be true. Therefore, the opposite is true, the thing I want to prove, right? So I'm going to prove that this is absurd. Well, by algebra, can I subtract b? Move it over by subtraction. What's 0 minus b? Think about it. Negative b. Now remember, we said earlier that a and b have to be what? Positive numbers. So we know this was positive, right? And we know this is positive. If you take a positive number and negate it, what do you get? What do you get when you take a positive number and negate it? Because that's what negative b is, right? It's a positive number negated. What do you get? What kind of number do you get?
Negative.
a negative. Now, why is this absurd that I just wrote down? Why is that absurd? Think about it. A less than negative b. Think about what A stands for. Think about what B stands for. Think about what negative B stands for. Yeah.
A is positive, so like it's weird because B is negative, it's still less than A.
She's absolutely right. Let me say it again, because words are hard, but math is easy. She's great at math. So, positive number less than a negative number. Can a positive number ever be less than a negative number? No, that's absurd. So we say this is a contradiction. We go, absurd!
I thought absurd is spelled with an O.
Nope, absurd. Absurd. Or we write contradiction. Or you can do these symbols. You can do an interrobang, that's what that's called. Intera, meaning interrogative, right? Like question, right? And then bang is the
Sounds like a
interrobang.
what?
Yep, it's called an interrobang.
That joke's forgetting.
There's a joke there. All right. You can also write this, an X with 4 dots here and here. That means contradiction. You can also write 2 arrows pointing inward at each other, which if you draw bold arrows like I do for math, then it looks like 2 smiley faces. Right? Contradiction. Interrobang. Right? Contradiction. Whatever you want to do. They all mean the same thing. Absurd cannot be true. So our assumption must be false, right? Therefore, our assumption, which was a plus b less than 0, is false. Therefore, if 2 numbers added together aren't less than 0, they must be greater than 0. Unless those numbers are 0, right? Well, we disincluded them. There should be a 1 here, by the way, not a 0. But that's okay. You guys don't know what it means anyway.
What do the E and the N stand for?
Okay, so this E means exists in. Remember thick letters, right? Dang, she thick. Remember the beginning of the year, right? Watch the first episode if you missed it. Thick letters, like thick N, means a set of numbers. So that's a natural number set. And I should have had a 1 there. Natural numbers starting at 1. So numbers you count your sheep with, like 1, 2, 3, 4, 5, 6. If we had a 0 there, it means natural numbers starting at 0, right? So I said, as long as they're natural numbers starting at 1, should be a 1 there, sorry. Then that's what A and B are, right? Any number that exists within that set. So would a half work? No, because it's not a natural number, right? Would 0 work? No, because it's not a natural number starting at 1, right? But would 5 work? Yeah, that works. A and B could be 5, right? Or they could be 6 and 3 or whatever, right? So it tells you what those are limited to be, right? A and B are numbers that exist in this set. So here's a collection of numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A and B can be any of those numbers. So they're both positive starting out. And then it becomes negative, we move it over. And that's a contradiction, because a positive can never be less than a negative. So therefore, our assumption must be wrong. Therefore, the opposite must be true. And we win, because that's what we wanted to prove. That's proof by contradiction. We assume the opposite and say that if okay, so what you're saying, right, if that were true, then all this would happen, right, which is ridiculous. Therefore, what you're saying is wrong, and the opposite must be true. This is used all the time in debates, right? Let's assume what you're saying is true, right? If that were true, then this, and this would happen. We all know that's not true. So what you're saying must be a bunch of crap. So the opposite must be true. That's proof by contradiction. Luke Millard said that if you want to prove that penguins can't fly, what you have to do is you have to take a penguin that represents all penguins, right? A variable penguin, if you will. Right? You can't just prove it for one number, you have to prove it for all numbers, so you have to prove it for all penguins. And you throw that penguin up in the air and assume it can fly. And then when it falls and dies, you prove that penguins can't. Right? You prove it by
I
contradiction.
think he needs therapy more than he needs math lessons.
That's not true. All right, so number 2. Prove the sum of 2 even numbers is always even. So think of 2 even numbers. Now, question, can fractions be even or odd? No, 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 no. Because whenever you divide a fraction by 2, it'll still end up being a fraction. Right? And when we say we divide something, right, for something to be even, when you divide it by 2, it has to come out as a whole number, right? Right, if you divide 6 by 2, you get 3. That means it's even because 3 is a whole number, right? If I divide 5 by 2, what do I get? 5 halves. Is that a whole number? No, so 5 must not be even, right? It doesn't divide evenly. So if you have a fraction, you divide it by 2, it's going to come out as a fraction. Did it divide evenly? No, because it divided into a fraction. Yeah. Yes, go. So we have 2 even numbers. And we're going to prove that when you add them together, you always get an even number. So think of 2 even numbers in your head, right? It has to be a whole number. It can be negative if you want. Add 2 even numbers together. Any even numbers you want. One can be negative, one can be positive. Doesn't matter, as long as they're whole numbers, okay? Integers is really what we're talking about. That's what this z means. Set z as integers. It's the positive and negative whole numbers. So negative 1's on the board, 0's on the board, 5's on the board, right? Just no fractions. Add them together. Do you get an even number? Add your 2 numbers together. Do they come out even? Yeah, they do. So we're going to prove that for all numbers. Are we good? All right. So given 2 numbers that are in the integer set, 2a plus 2b is even. Now, why did I write 2a and 2b? What's our definition of an even number? It can be divided by 2. Can 2a be divided by 2? Yeah, because when I divide it, what do I get? And a is a whole number, right? So whatever I divide that to, it'll give me a whole number, right? Which means this must be even. So 2a plus 2b, we know for a fact that this must be even, and this must be even. Now, we're going to prove that our answer, let's call our answer C, must be even. And here's how we're going to prove it by contradiction. We're going to assume that our answer isn't even, right? We're going to assume the opposite. So we're going to assume that C is what? Odd. So assume that 2 even numbers add up to an odd number, right? This is our first even number, and this is our second even number, right? How do we know that they're even? Well, we can divide it by 2, right? Guaranteed. So I'm going to prove that C can't be odd, that it's absurd, right? Here's what I'm going to do. I'm going to pull out a 2 from both. Everybody cool with that? All right. What?
I remember doing that last year.
Okay, if I were doing this, you distribute, right?
Yeah, distributed property.
Right? Now, distribution in reverse is pulling out. There's a joke there. Yep. All right, so here we go. Now I'm going to divide everything by 2, so I get a plus b equals c over 2. Now there are 2 cases here that I'm going to explore. Case 1, c over 2 is not an integer, meaning that it's not a whole number essentially, right? So if I divide c by 2, it comes out to a fraction is what I'm saying, right? C over 2 is a fraction. Here's the problem. Aren't a and b whole numbers? Can you ever add 2 whole numbers together and get a fraction? No. So if c over 2 can't be simplified, then it's a fraction, not an integer, right? And we have 2 whole numbers adding up to a fraction. Can 2 whole numbers ever make a fraction? No. So this is absurd. Contradiction. Can't be, right? So c over 2 must simplify, right? Which means c over 2 is an integer, right? Well, if c over 2 simplifies to a regular number, right, not a fraction, pretend c was 4, right? 4 divided by 2 is 2, right? It simplifies to a whole number. Well, if it simplifies to a whole number, that means when we divide it by 2, we get a whole number. And if you divide a number by 2 and get a whole number, what must that number be? Even, right? So that means, therefore, c is even. Well, wait, hold on. We assumed at the beginning, what about c? That c's odd. So we have a contradiction with what we assumed. So that's a contradiction as well. That contradicts what we said earlier.
Wait, I have a question. When do you contradict the second step then? Instead of like that C is even?
Hold on 1 second, Mark. I'm going to get back to that. I think I know what you're asking, and I'm going to show you what's going on. So, we contradicted that this is an integer, right? It can't be an integer because if it was, or sorry, if it was an integer, let me repeat. C over 2 can't be an integer because if it were, right, it would be even. And we said it had to be odd. So it contradicts our earlier thing. So we have a contradiction. It also can't not be an integer, because if this weren't an integer, it means it doesn't simplify. And when do you ever add two whole numbers and get a fraction? Can't be true. That contradicts, right, how math works. So it contradicts our assumption, which means our assumption must be false. So 2a plus 2b can't equal an odd number. It must equal an even number. Therefore, by contradiction, C is even. And more importantly, 2a plus 2b is even. Did it?
So basically what we're doing here is we're taking all possibilities that can...
And proving that, look, if what you said is true, then this and this must be true. One or the other, right? I'm going to tell you right now that neither of those are possible. So what you said must be false, right? So the opposite must be true. Does that make sense? Right? What you said was absurd. Look, if that's true, then all this crap has to be true. And it's not. So what you said must be false, which means the opposite is true, and I win. It's a good debate technique, right? I hear what you're saying about all this stuff. Sounds great. But if it were true, then this, and this, and this would be true. We all know that's a bunch of BS, right? So what you're saying must be false. So the opposite must be true. Okay? Are we feeling 50% on this? Like, sort of getting the concept. Right? I think the penguin thing makes sense. How do you prove penguins can't fly? Well, I can prove that if I assume they can fly, that doesn't make any sense, right? Because when I throw the penguin, it doesn't fly. It dies.
Why does it die?
Well, because when I throw penguins, I throw them from, like, buildings.
Why?
If you're going to do it, you got to be thorough.
But what about
It's for the math. What if I didn't throw it from a building? Maybe
What if
it
they
just-
can phase to
if
a wall?
it knew it could live, it would just fall and just like, oh, no, right? Maybe it just doesn't care about falling and getting hurt a little bit. But all things want to preserve their life, which means if I threw it from a building and it knew it was going to die, it would fly if it could. Because all things try to preserve their life. This is for science. Well, not all things.
All right,
Stop it. No.
now-
Natalie, no.
For
All right.
science, I'm going to hit my head on my desk really hard, and if I...
No. Sit down. All right. So here's how we're going to prove. So, if we want to use contradiction. All right, I know, it's funny. If we want to use contradiction to prove that the Cevians are concurrent, what are we going to assume first? I'm on page 5. If we want to prove that the Cevians are concurrent, and we're going to do it by contradiction, what do we have to assume?
Mr. Mack, I taste pain.
No.
That they don't equal one.
Nope, hold on. If we want to prove this, we're going to show that the opposite of this doesn't make any sense, right? So I'm going to assume that they're not concurrent. So assume AE, BF, and CD are not concurrent. Assume they're not concurrent. That means our diagram is misleading because it looks like it goes through G, right? So here's what I'm going to draw, and it's going to be kind of weird to see this because my diagram does have them intersecting at G. We're going to assume they're not, right? Cool? So if that's true, that they're not concurrent, there should be some line that intersects them that is concurrent, right? If I've got two lines, and this line isn't concurrent, right? Shouldn't there exist a line that would be concurrent with these two? This one's staying with me. Right? So if these three aren't concurrent, well, at least two of them will intersect eventually, right? So let's say that this line is concurrent with the other two. And I know you're thinking, like, it is obviously not because you drew it that way. But let's assume it is, right? If these aren't concurrent, there must be some line that is. So let's let this line be concurrent. Yeah, not congruent, concurrent. It's okay. So I'm going to create a line, CX, and I'm going to say, then there should exist a line that does make it concurrent, and I'm going to let that line be CX. So we're going to assume that CX AE and BF are concurrent. So this is all our assumption right here. Okay? We're going to assume those aren't, and that there must be some line that does intersect them, right? I know my diagram looks really weird, so focus up here. I'm going to assume those three lines aren't, so there should be a line that does be concurrent with the other two, right? Where is it? I don't know. I'll draw it, right? But it should exist, right? There should be some line I can draw. I'm going to say that's the line. Now we know this is absurd. I'm going to show you why it's absurd, okay? So, we know by Ceva's theorem the bases of the triangles that are formed by the concurrent lines, when you multiply them together, you get 1, right? So AX is that base, right? I'm using big letters. Over XB should equal BE. Is there an easier way to write BE? There is in this case, little c, right? Over EC, little d, right? Little e, little f. Are we cool with that? Right? By Ceva's theorem. If they're all concurrent, which we said they were, right? Then these guys over each other equals C over D equals E over F. We cool with that? Now here's the problem. Didn't they tell us? Oh wait, sorry. My bad. Not equal. Multiply. I did this twice in a row. Ceva's theorem says they multiplied equal 1. Right? Multiply. My bad. They multiplied equal 1. Here's the thing. Didn't they tell us that A over B times C over D times E over F also equals 1? So A over B. What's another word for little a? I want to use big letters here. AD. So they gave us that AD over BD times C over D times E over F equals 1. Right? That's basically what they gave us. I substituted little a and little b for these guys. Okay. Now, here's the thing. If this equals 1 and that equals 1, don't these two things equal each other? So therefore, AX over XB times C over D times E over F equals AD over BD times C over D times E over F. Now, here's where it gets weird, right? Or absurd. If this is true, then when I divide this side by EF, I have to do it to both sides, right? When I divide this side by EF, what do I get? 1, right? Anything divided by itself is 1. Now I got to do it to this side too. Oh, look, there's already an EF there. So when I divide that by EF, what do I get? 1. When I divide both sides by CD, what do I get? 1 for both, right? It's nice when they're on both sides, right? And so I get this times 1 times 1 equals this times 1 times 1. So that means AX over XB equals AD over BD. Now let's look and see what that means. You guys cool with this so far? What is AX? Well, it's this amount, right? And BX is this. What's AD? It's this amount. And what's, oh, sorry, that was AD. What's BD? This amount. So you're telling me that AX and XB are the same as AD and BD. In other words, what we're saying here, here's a board, okay? And our board is thin, infinitely thin, so it's basically a line. If I want to cut it in half, I can do that, right? Let's call that point X. Then I say, I challenge you to cut this board in half using a different point. Don't use point X. You can't, right? So this doesn't cut it in half, but it cuts it into some ratio, right? Maybe it's 2/3 and 1/3. And you're telling me that this is also 2/3 and 1/3? Look, that's smaller. If this is 2/3 going to X, how can that be 2/3? The only way that could be true is if D and X are the same point, right? If they're the same point, then they would be equal, right? It would go all the way to here. So this is a contradiction. That means X and D are the same point. Therefore, X and D are the same point. And if they're the same point, didn't I assume that CX was concurrent? And if CX is the same as CD, then CD has to be concurrent, doesn't it? Let me say it again. X and D have to be the same point. It's the only way to make this true, right? If that was a D and that was a D, we'd have the same thing on both sides, right? This one just in reverse. X and D have to be the same. If I gave you two equations, is there any way for X and Y to be different numbers? No way, right? X has to equal Y. Here's this equation. They equal each other. X has to be the same thing as D, right? Has to be. AD would be the only way to make AD, right? So X must be D. And XB has to be BD. So X must be D. X has to be D. They're the same point. And if they're the same point, right, and I made a concurrent line, if CX and CD are the same line, and I said CX is concurrent, that means CD must also be concurrent, because it's the same line, right? I'm telling you that this line and this line must be the same. So this line that I drew to make it concurrent must be this line. So now I know that AE, BF, and CD are concurrent. And that's what I wanted to prove. So I assumed that they weren't concurrent, which allowed me to say, well, there must be some line that makes them concurrent, right? And I proved that that line can't be it. It's impossible. In order for that to be true, by Ceva's theorem, those lines would have to be the same. And I said they were different right at the beginning. So assuming that this wasn't concurrent is impossible. It has to be concurrent, because this line is, and they're the same line. So they're concurrent. If I've got you about 50, that's good. This last little bit's kind of weird, and it's because my diagram, I had to draw it kind of strangely, right? Because this one we know is concurrent. We had to show it was absurd. So you should feel a little weird about that, like the diagram looks weird. Because it is supposed to be absurd looking. We assumed that this guy was the concurrent line. If this guy wasn't, there has to be some line that is, right? And we showed how absurd that would be for that to be concurrent, right? It would break Ceva's theorem. In Ceva's theorem, when they're concurrent, we get this relationship, right? So if this breaks Ceva's theorem, it must not be concurrent. Now we chose this line to not be that one. It could have been any line, right? So this line must be the one that's concurrent. There you go. So, good news, bad news. Good news is, well, let's talk about the bad news. The bad news is this is weird. It's different. You're not used to it. It's going to take some time, like Katie said. The good news is this is not impossible. It just takes your mind getting used to it. It's different. It should feel weird. You should feel about 50%, like I see it, but not really, right? And it'll get better over time. Okay? Hang with it. Tomorrow, we're going to grade our quizzes in class, which means your one shot to complete your test, right, because you didn't have enough time to finish it totally, is today. If you have a class that you're not doing anything in, ask if you can come in here. If you got a homeroom, whatever. I don't care if I'm teaching already. Sit in the back. If you're in a homeroom every day and you're bored out of your mind, and you're like, I'm not really getting geometry, come in and watch geometry during third hour, if that's your homeroom. Or during first hour. Or during sixth hour. Get 2 doses of geometry so you can ask questions and keep up. I had a lot of kids that did that at Sandwich because they were bored in their study halls. They just come in and watch. Worst case scenario, you're in here and you got nothing better to do. I'll help you TA, kind of like Zayden did, right? You can do that, and then I'll give you self-development points. Okay.
Wait, so if you like pick someone to teach, if you got self-development.
Yeah, so like if you've got nothing going on in 6th hour, that's my only geometry after this. You've already learned today's stuff in theory, right? You can help me TA it in 6th hour.
Okay.
If you've got a study hall or something going on, right? And I give you self-development for that. Now, because you guys are 4th hour and 6th hour really get screwed because they can't really teach anybody because they haven't learned it yet for that day. But you can still come in the next day and help kids, right? Potentially. It's better than just sitting in the study hall with nothing to do, right? Come on in. I don't care if I'm teaching a class. I don't care if it's algebra, right? You can TA in that. There's stuff in algebra that I'm sure you guys never got to because I really push my kids really hard, but, you know, like when I showed you this stuff, these symbols, right? My algebra kids know what that means. That's okay. Come on in, learn. Get some algebra refresher. Or sit in basic geometry. help then, right? That's all we're doing today. Tomorrow we'll get to angle bisector stuff, but we'll squeeze that in right at the end after we grade our quiz. Make sure you come in and finish your quiz today, okay? It'll make the grading a lot easier on you tomorrow. Guys, you know that the incenter and the circumcenter are both formed by bisectors, right? Perpendicular bisectors form the circumcenter. Perpendicular bisector, really long word. Circumcenter, really long word. Circumcenter means circle goes around, right? Circum, like circumnavigate, right? Angle bisectors make the incenter, the other circle center, right? In center, center of a circle inside, which means there are radii going out at 90. That was terrible. Sorry, there should be a circle there. Right? It's doable. It is. Study up. Make sure you finish early.
Yeah.
What time is it right now?
It's 30.
Yep. Go ahead. Good job, today, guys.